Okay, so I'm on the wrong section. There we go. So, I guess before I begin, are there questions on anything? Anything covered last time? Or you want to ask? No. So, well, I'm gonna finish up the last page or 2 pages of this problem set, and this time we're looking at something slightly. We're not entirely the same thing as before. So, on Tuesday we worked on this process of use substitution for integrals, and today, I mean, our work might involve doing use substitution for some of them, but actually we're kind of focused on something a little bit different, or at least for the first page, it's different. The first page is actually about areas between curves, what the topic is normally called. So, yeah, well, I need to charge. Yeah, so let me at least describe what that is pictorially. It's not so bad to express. So the idea is, say you've got like some function on top and you've got some other function below, and you're trying to calculate some area. I guess I'll shade that with a different color. You can't really see that it's a different color. And let's just extend like the intersection points down to the x-axis. And so we would say like that this is going from point A to point B. And the idea is that the area between the two curves is going to be expressed as some integral. You would expect the A to B. And then the thing is like, what is the function you integrate? Turns out that's going to be the difference of the two functions, where you always do the top function minus the bottom function. So it's going to be f of x minus g of x in this case. And so this is how you would compute the area between the two curves. And if the situation is such that the functions are better described in terms of the y-axis, if they're like functions in terms of y instead of x, I guess the easiest example I could draw for this would be something like if this was one of the functions, and say maybe that's another function, like so that's f of x, that's g of x, and then the area is like that, and then you actually have like y from A to B, let's say. You can still do the difference of the two functions, top minus bottom, but you have to just kind of tilt your head sideways in order to see which function would be considered on top in this case. It's which function actually gives the higher x value in this case instead of y value. And one of the problems actually does work like that. It is written in terms of y. Yeah. All right. So I don't know if there's really anything else I can say about this conceptually. So let's just go ahead and do at least the first 3 problems are basically just this kind of material. Okay. So for number 3, find the area bounded between these curves. So without drawing what this looks like, I wouldn't know how to start. So like, yeah, it's a good idea to always sketch whatever the problem is actually stating. So y equals 1 is some kind of horizontal line. X equals e is some kind of a vertical line. Just mark that as e. And then you've got this 1 over x. So you kind of know what that looks like at least. Let's say that that's 1 here and that there's like a point there. Then and then if you plug e into this, you're going to get 1 over e. That's less than 1. Don't know what that is exactly, but we can at least put another point there, and we can kind of say like what the shape of the 1 over x function would be. Okay. And so now this tells us what the region actually is. It's this little piece right there. Well, you could draw it so that it doesn't look quite so little. And the point is then, well, this diagram tells us everything about what the integral actually should be. So we're now able to say what the integral is. So you can see like the two, well, not two curves, but the curve, you would say that it starts at x equals 1 and then goes up to x is equal to e. And so the integral is going to be from 1 to e, and it's going to be an integral with respect to x. And then you would do top function minus bottom function. The top function in this case is the 1, and the bottom function is the 1 over x. So there we go. This integral is going to calculate for us the area between the two curves. And so then you just would go ahead and crank this out. So this is x minus ln of x. You could put absolute value of x. Turns out that the absolute values are going to disappear when we plug things in. Okay, so this one isn't so bad, so I can just manually compute this. X minus 1 minus 1 minus 0. So that's going to be e minus 2. At least one of the problems, I gave up on computing it by hand because it was just going to be a pain. That was number 5, it looks like. But yeah, but 3 and 4, at least I'll show you how to do this by hand. Okay, so that was 3. And 4, well, you're gonna have to draw it, maybe. And it might be a bit hard to draw this. I mean, you can kind of tell that like these are going to be parabolas, but in order to kind of, it might take a bit of practice to get used to thinking about things kind of sideways like this. But the x is equal to y squared is kind of the standard parabola that you'd expect. Maybe make that a little bit wider. But then this x is equal to 8 minus y squared. You should think of this as this parabola that's opening downward that is kind of starting at 8. So just imagine that this is instead like replace the x's and y's, then you know exactly what that looks like, and you just rotate that image that you have in your mind. So we know its vertex is at 8, and I think that's really all I would do in terms of accurately drawing this. So now we know what this picture is. It's this area between these two parabolas. Well, what's important in terms of describing the integral, though, so we can clearly do the top function minus bottom function, but what we need to find is what are those, what are the limits of this area here? What are these parts that I'm labeling in blue, right? And so this I would probably solve for algebraically. So we know that, well, these are the intersection points of the two functions. And so that means that we need the y squared has to equal the x minus y squared, which I can just write, which means that 8 is going to be equal to 2y squared, which means that y is equal to, well, y squared is equal to 4, which means y is equal to plus or minus 2. And so the tick marks in blue are actually corresponding to positive 2 and negative 2. Okay. And so now we can set up the integral completely. So it's an integral from -2 to 2 with respect to y. I'll say dy. And the top function is the parabola that starts at 8. So it's going to be this 8 minus y squared. And then we subtract off the bottom function, which is another copy of y squared. So this is the integral that you will compute to get this area. And Well, I think you can just also crank this out. So let's see, this is going to be minus 2/3 y cubed, right? So you would think about the 2y squared, you would integrate that, so you get 2/3 y cubed. And then we are evaluating this from minus 2 to 2. I don't know. 16 minus 2, 4, 8, 6, 16 over 3. Yeah, 16 over 3. If I plug in -2 in, I'm going to get -16. This is going to become a plus 16 over 3. So we see that each of these things are kind of going to be doubling up. So it'll be 32 minus 32 over 3, which is going to be 64 over 3, I think. 32 times 2 and then divided by 3. 64 over 3. Yeah. Okay. Any questions so far? No questions. Fine. And then, well, number 5. So this is actually a bit of a pain to work with, this polynomial. Turns out this guy doesn't factorize or anything, but when you subtract this with that, that will factorize because of the hint. So there's only really there's only like one piece of information that we need to know about the graph of it. So I think that it's kind of excusable to maybe just throw this into like a graphing calculator. So I'm just going to try to sketch what you get as a result of that. 2, 3, 4, 5. So here's 4, there's 5. The way that this looks like, let's see, it's got a point here, it's sort of down here, it's sort of up here. It's a bit wavy. Oh, okay. The important part that we actually want to capture is, okay, so in red, this is the region between the two curves. Okay, the second curve is the line, which maybe is not so easy to see here, so I'll use a different color for that. Okay, the important part of actually having the picture of this is to know like that the integral that you would set up, it is actually going to be split at the intersection point there, because at that point the top function and bottom function end up switching, and so that's really all you need to know from the graph, that and knowing which function is on top for the region. Yeah, so you could compute it by other means as well, but yeah, just having that is enough. And we know that, so okay, I didn't align things up perfectly, but the this point is supposed to be 1, that's supposed to be 2, and the other intersection is supposed to be 4. Okay, so it ends up being integral from 1 to 2 of, and then in this case, the top function is the quadratic, or not quadratic, the cubic. So then you have that, and then you subtract off the line. And then you need to add to that the integral for the other half of this region. So that's going to be an integral from 2 to 4, and the top function in this part has the line on top and the quadratic on the bottom. So the function that you end up integrating ends up being the negative of in the other integral. Okay, well, and so this is where I didn't want to show all the little steps here because I think it's kind of clear what you have to do. You have to expand out or simplify out what that polynomial is, integrate it, and then evaluate it. So I'll let you show like all the detailed calculation for that. I would say that like, yeah, if you don't do that, you're not going to get full credit for this because the grader is going to check that you actually do show a decent amount of work. And I'm just going to skip right to at least telling you what the individual parts of the integrals are going to be. So if you calculate the first integral, you should try to do it by hand. You'll get 5/12. And if you calculate the second integral, you'll get 8/3. And so then the final answer for this is going to be 37/12. Okay, so that's the answer that you should get. Right. Are there any questions on how you would actually go about computing these two things? Yeah. Okay, good. Right. Then, right, this last page, it's a bit more, I don't know. I don't know what to say about this last page. So, okay, average value, well, there's a formula for it. So in general, like what you'll see, if you look up what it means, like average value on some interval, let's say like average value for a function f of x on an interval a to b. Let's say it should be a closed interval. Maybe it could be an open interval. Doesn't really matter. But the formula that you'll see is b minus a integral a minus b f of x dx. Okay, so you'll end up seeing this kind of thing. And I guess what I want to do is to explain this formula so that you don't actually have to memorize it, but instead so that like it's kind of a clear formula that just kind of makes intuitive sense. So the way I want to relate this, I want to relate this to average value that you would normally have just like in the discrete kind of case. So where you just have like a set of numbers. So hopefully you remember like that if you have like a set of numbers like I don't know, x1, x2, x3, dot dot dot, xn, a bunch of different numbers, and then if you're asked to like then take the average of this set of numbers, like how would you do that? Well, what you would do normally is you would add up all of those numbers, and then you would divide by the number of numbers that you have. So we could denote this like as using sigma notation, so sum, and then you would say like then divide by the count, how many numbers there are. So you divide by n, and then if you've maybe you've seen this notation, maybe like I don't know. You don't necessarily need to take statistics, but this kind of thing shows up in like pre-calculus. So some people call this X bar. This is also called the mean. This is called the average, right? So hopefully some of you recognize this. The idea is this formula is basically this formula. It's like this average in this discrete setting where we're just talking about individual numbers is kind of just like a different version of this average value in the continuous case where we have like a whole function's worth of numbers, but they're all like weighted very, they're kind of weighted in a different way. See, like this, the way that this scaling works is it's kind of trying to divide by n in a sense. It's dividing by the length of the interval. And this integral is acting like the summation. So it's very, I don't know, I think it's very intuitive that this formula, it makes sense as being the average value because this is the way the average value is defined in discrete sense. Well, this is how you define it in the continuous sense. Okay. Yeah. So that explains the formula, and we just need to calculate average value for this function for this interval. So that is just going to be answered by computing this integral, 2 sine x plus e to the x over pi. Okay. Well, first term is going to be minus 2 cosine of x. And second term, so this is where in the previous days of homework, like this would have been use substitution. But we're going to try to just think about this slightly differently so that I can avoid overcomplicating this problem because it really is kind of simple. We can use kind of a technique of guessing and checking in a way, right? So you know that the core of this of integrating this is going to have this exponential, right? In the exact same way. The only thing is like, you know that because if you try to take the derivative of this, something is going to pop out that needs to get canceled in order to arrive perfectly at this exponential here without a coefficient in front. And so you just think like, what does taking the derivative of this introduce? Well, it's going to have a 1 over pi pop out that needs to end up being canceled away. So that means that you need to multiply this by pi. Okay, so multiplying by pi, then you can check that taking the derivative of this second term is going to give you the exponential that you want. So there we go. That's the integral. Okay, and now we just need to evaluate this. Well, I can probably shortcut this in another way. Yeah, I'm gonna also shortcut this in. Oh wait, I need to put a 1 over 2 pi in front. Great. So 1 over 2 pi in front of that, 1 over 2 pi after or outside of evaluating 1 over 2 pi. Okay. Now what I want to do is I want to explain that this term disappears in the evaluation. So this time I'm evaluating it slightly differently. Instead, I'm thinking of splitting the evaluation over the terms inside, and I'm noting that when you plug in 0 versus when you plug in 2 pi, this cosine function is going to be the same number. It's going to be 1. Right? It doesn't matter what the number is. The fact is that evaluating at these two is going to give you the same number, but then you're supposed to subtract off those two values. And so evaluation on this term cancels. And so I only need to consider evaluation on this other term, pi times an exponential. Oh, oops, don't want to use a different color. Okay, so on this term, we end up, let's see, this will be e to the 2 minus e to the 0, which is 1 times pi is pi. And so, well, we can cancel the pi's. That's fine, I suppose. We'll have a 1/2 e squared minus 1. And yeah, that looks good. Okay. Right. Any questions on that? No? All right. Then so 7, car's average velocity is given by this function. And we're talking about hours after noon, which these are. What is the average velocity between those two values? So it's just dressing up the same kind of problem about average velocity. So between 2 and 4 p.m. just means the integral is going from 2 to 4. And the velocity function is what we're trying to take the average of. So that velocity function is the thing that goes inside the integral. And I'm writing dt because the function is in terms of t. And lastly, we need to weight this thing. We need to end up dividing it by the length of the integral. So this 1 over 4 minus 2 is going to do that for you. Okay, which then we can just go ahead and integrate it. 40t. This term, I hope it's clear. It's 100 ln of t plus 1. Yeah. So normally, I guess, or not, maybe not normally, but like in the section from previously this week, we would have done like a u substitution because there's a variable on the bottom. We would end up like using u is equal to t plus 1 in order to see that this function is essentially behaving as it behaves as 100 over x, basically. It behaves like that. And then, of course, you can factor out the 100. So it behaves like 1 over x, so you know it's going to be an ln. But really, introducing a shift like that is kind of something you can just immediately glance at and realize that that's not doing much of anything. So you can just create that right away. Yeah, I mean, if you wanted to perform the u sub just to double check, you can do that as well. But yeah, this is what you would get. And you can check by just taking the derivative and seeing you arrive back at this function. So we need to evaluate now. And yeah, it's still doable by hand, this one. Okay, so if I plug in 4, I'm going to get 160 plus 100 ln of 5. Maybe I'll put parentheses around that. And then if we plug in 2, it'll be minus 80. And the second term is going to be 100 ln of 3. Okay, so this is now, now I just need to simplify this a little bit. So 80, and then, okay, so to simplify the logarithms, I would rather use a logarithm property. So you should know that the difference of two logarithms is going to turn into like a division inside, I guess is what you could, how you could say that. So this ln of 5 minus ln of 3 is going to become ln of 5 over 3. You can view that as one single thing. And then, of course, you don't want to have that 1/2. That's kind of your in the way in a sense. So we can simplify that just a bit more. That'll be 0. Okay. So this is the nicest way you could write this result, I think. And okay, so maybe you could figure out what the decimal value is, since this is actually supposed to be what, miles per hour. Maybe I can put units off to the side somewhere, since this is supposed to be, yeah, a velocity. Make the box a bit wider. Then. Okay. And then 8 is the last problem. So good. Fred's velocity, Marie's velocity. So for A, we are just going to compute this integral. That's a computation. Interpreting it is a bit wordy. This is 30t plus sine of pi t, and then subtract off. Actually, so let's just simplify that a little bit. So this is supposed to be 10t minus, and then a cosine of pi t. dt. Okay, so this is the thing we're integrating. And well, it's going to turn into 5t squared. The sine is going to turn into a minus cosine. And because there's actually a function, sort of a function inside it, like if you were to perform the u sub for this, you would let u be the pi, u be pi t, u be the thing inside of the function. That way, it ends up being easier to think about. But the alternative way I'm trying to show or explain to you is that you know that like you just need to adjust this function by some kind of scale factor to cancel out something that pops out from taking the derivative. So if I take the derivative of this, I end up very, very close to sine of pi t. The only thing that sort of occurs is that there's a chain rule that's going to pop a pi out. So the derivative of this is going to end up having a pi in front of the sign. We want to cancel off that pi that comes out. We want to divide by pi. Okay, so it's like these kinds of things that you could do via u sub. They're so simple that you really can avoid using u sub at all, as long as you just kind of think about it. I don't know, you get used to it. So I don't know if anyone is confused, since no one is saying anything, but hopefully you're not confused. Hopefully it's straightforward. And so the other term is done in the same way. So you see that a pi will pop out from chain rule. You're going to cancel that pi by dividing by pi. And so this is going to give you the cosine pi t that you want inside the integral. And then we just evaluate this from 2 to 5. Looks like I did that by hand. I guess that's fine to do it by hand. Okay, right, so 5 times 25 minus, if I put in 5 pi, that's the same as just pi. Cosine of pi, wait, 1, 2, 3, 4, 5. Yeah, so this is, cosine would give you -1, so then this is going to become plus pi over, yeah, plus 1 over pi. Sine is going to be 0, which I think I'll just denote that as being +0. Then I'm going to subtract off the evaluation at 2. So this is going to be 5 times 4. Make that look like multiplication. Plugging in at 2 is going to be the same as plugging in at 0. Cosine of 0 is going to be 1, so you end up with a minus pi. And sine is going to evaluate to 0. Okay, and then the thing is that, so this is going to be 5 times 25 minus 4. And then you've got 1 over pi, and then actually this is also plus 1 over pi, so you have 2 over pi. This is 21, which you can then multiply by 5 by dividing it. So this should be 105 plus 2 over pi, I think. Yeah, good. That's what I got the first time. And this is in terms of something. So we're integrating velocities, so we should get a distance. So this is meters. Right? When you integrate velocity over time, you're gonna cancel out the division by time. So you get meters. Okay. Now for part B, interpreting what this integral actually means. So this is where you maybe think about it a little bit. The idea is that, well, each of the individual subtractions here are measuring something. They're measuring the distance from Marie to Fred. And then what happens then when you integrate all of these differences? What happens is it's measuring like the net change that you end up getting. So like if you start, it's like you take a snapshot at the 2 minute mark, and then you take a snapshot at the 5 minute mark, and you end up just comparing what has happened. So this VM minus VF at the 2 minute mark would, denote that difference. And then at the 5 minute mark would denote another difference. The integral over that is going to be what happened when you go from 2 minutes to 5 minutes, um, how their separation has changed over time. So the way I would phrase this is I would say this is the net change in distance between the two people, Marie and Fred. Just Fred, right? Yeah. And of course, if you're going to answer this fully, you need to also say like between the time. So from minute 2 to minute 5. Yeah, I don't know how else to say this. So, all right. Are there any questions? No? Okay, well, I'm going to stop the recording.